Okay, let me start the talk with an executive summary. In the first part of the talk, I will argue that computing has grown big and out of control. We need consensus, but it is challenging. And I will close that part with an overview of the solution space and will argue that we need language-based solutions. In the second part, I will present one such language-based solution, the REScala programming language that we have been developing with my team in Darmstadt. Now, in the beginning, computing was simple and ordered. We had Turing universal machines and we had von Neumann architecture, the von Neumann architecture that realizes the Turing theoretical model. The machine is very simple and ordered. Instructions are ordered in a list. Memory is ordered as an array, and instructions are executed in the order in which they appear in the list and communicate with each other via mutable state stored in memory. But we soon left this simple and ordered world, and by doing so we lost simplicity and universality. And this was when computing went big. I'm reusing here statements from the Popple keynote talk 2021 of Rashid Geraoui. He coined this term of computing going infinitely big, which was to cope with failures. We replicated computations across connected computers. The ARPANET and the internet was born. But because of this move, we lost universality, meaning that problems that were solvable before turned to be unsolvable unless we implemented consensus, which, even if solvable under realistic assumptions, is very challenging. We will come to talk about this in a minute. Now, essentially the same problem occurs when we go infinitely small, when we have to put several threads and several cores within one machine. Again, we need consensus between these cores and these threads. Now, where do we stay? Where do we stand today? Our computing today is very different, actually, from that traditional big that Rashid mentioned. Traditional big machines are the geo-replicated data centers and clouds. In this picture here, they are, so to say, in this right upper corner, the clouds, the far end. Computing on those machines actually operates in a rather controlled world managed by distributed systems experts at big tech companies. Today's computing infrastructure consists of millions of devices in the front end, connected to each other, but via the near end also connected to the far end clouds and data centers. Distribution is now not only a matter of enabling availability and scalability, it is an inherent feature of the world. People and devices are distributed. Likewise, concurrency is not only a matter of speeding up computations, it's due to people and devices acting autonomously in time and space. Moreover, we see a trend towards decentralization of computations, moving computations to the front end and near end. This is because decentralization is good at supporting offline availability, low latency, efficient use of communication resources, or it enables user-controlled data privacy and even more. But what this means, the whole story here of this slide is that today's big computing has gone out of the control of specialized engineering teams at big companies. Computations running on these new internet scale machines like social apps or collaborative workflows or real-time businesses and more are out of control in a different way. The point is they are interactive and data-driven. Why do I say this makes them go out of control in a second way? Well, this is because the order of computations is now not determined by the order of the instructions of the program, but rather driven by the arrival of data and the arrival of events. So there is a mismatch between the order of the instructions and the order in which the data flows. Our answer to this inverted outside-in control has been callbacks. So to model reactions, we attach callbacks to events. And this modeling has been accused for causing what is called the callback hell, meaning causing complex and error-prone designs, easy to get inconsistent. What's the problem? Well, there are two problems. The first problem is that the application developer is now, I say, playing compiler. He or she is responsible for implementing the callback interfaces, their registries, for managing their life cycle and managing the application consistency as part of the application logic. This results in bloated code, but moreover, it results in complex control flows which are hard to reason about. The thing is that conceptually coherent logic is split in several callbacks that coordinate their execution via broadly scoped variables. So, to summarize, computing is big and out of control. Disorder is the norm. State is broken, or broken state is the norm, and this is not very new, but the open, dynamic, and interactive nature of today's distributed applications, which are in the focus of this talk, amplifies the problems. Moreover, I said we can't rely on skilled teams at big tech companies to get the application correctness right if we embrace decentralization. The traditional answer to disorder and complexity has been strong consistency guarantees of coordination protocols like Paxos and two-phase commit and computational models like bulk synchronous processing. Let me use the database transactions to illustrate how coordination protocols establish order. In essence, there is some theory behind them, so serializability in case of transactions. And based on this theory, the protocols engineer or create the illusion of order and do so in a transparent way, meaning by guaranteeing application correctness by design. And this is, of course, a great feature. But, as you all know, it comes with a price. And this traditional answer, the strong consistency, has been challenged. For example, in the CAP theorem, which basically tells us if we we can't have consistency without sacrificing either availability or partition tolerance. And for our interactive distributed applications that are in focus here, we can avoid losing availability, and partitions are basically a given for the new big internet scale computing systems we are talking about here. So we need to do something about consistency, and James Hamilton captures what we need to do very nicely in his quote, where he says that we need to reduce consistency mechanisms down to a minimum and make them as hard as possible for application developers to use them. Why? Because they are difficult to use in a proper way. The result was the emergence of many NoSQL technologies, which basically dropped strong consistency and replaced it by design patterns, if you want, kind of using commutative and inverse methods and compensation. In terms of the practical engineering, this makes it very easy to scale infrastructures, but it's tricky to ensure application correctness. This may be okay if you have skilled engineering teams implementing both the infrastructure and the application, which was the case at that time at Google or Amazon. But to democratize the development of massively distributed applications that operate in a decentralized manner, we need to get correctness guarantees back out of the box, but in an affordable way in terms of performance and availability. So how can this be possible? Well, by exploring the spectrum between strong consistency and no consistency. Even Eric Breuer, who formulated the CAP conjecture in the first place, has warned us not to take it literally. He rephrased his formulation in 2012 and highlighted that there is a lot of flexibility out there that we can make use of. And what he means by this is that different applications have different needs. First of all, there are problems that do not need consistency. It can be solved in a distributed way without consistency. Second, there are problems running on infrastructure with stable connections, like in data centers. There you can have both. You can have availability and consistency, because partitions are rare. There are cases, of course, where strong consistency is just needed, or where you need to do a systematic trade-off between availability and consistency. And that's what he kind of formulates as the modern goal of CAP, is to maximize combinations of consistency and availability that make sense for a particular application. So this is a very constructive and positive reformulation of the CAP theorem, but the problem with it is that it leaves the responsibility to maximize combinations of availability and consistency with application developers. And I argue that this is too much of a responsibility for application developers. Recall Hamilton saying or telling us, make it as hard as possible for application developers to get permission to use consistency mechanisms. So we, for the sake of correctness and productivity, we are in need for new affordable illusions of simplicity that automate the combinations of consensus and availability. To illustrate, I borrowed this picture from Grady Butch's book on OO design. It says that the task of a development team is to create the illusion of simplicity for the user. I'm reformulating it to say that it's our responsibility as researchers, as systems and programming language researchers to create new affordable illusions for software developers. And in fact, the problem is being handled from different perspectives, and from different communities. So there is work looking at what I call a theory of asynchronous problems, trying to find out what is the class of problems that can be solved in a distributed way without consensus. Then there is work on replicated data types, kind of building blocks that make it easy to construct systems that combine consistency and availability. And then there are formal reasoning methods that enable us to reason about properties of different combinations of consistency and availability. And my statement here is that programming language research has to play a key role here in bringing these different perspectives together. And when I say PL-based solutions, I mean languages that provide developers with abstractions to manifest enough application semantics so that the language machinery can automatically reason and make decisions about proper combinations of availability and consistency. And now in the second part of the talk, I will present one such language-based approach. As I mentioned in the beginning, REScala, a language for interactive distributed applications that we have developed with my team, the REScala team on this slide, as part or in the context of an ERC Advanced grant. The rest of the talk is structured as shown in the slide, so I will start by explaining the basics of reactive programming, reactive flows. Then in the second part, I will present the so-called serializable concurrent flows, then partition tolerant flows, and then at the end, I will bring those two last things together in what I call hybrid flows. But let's start first with the basics. So REScala supports what is called reactive abstractions. There are two kinds of such reactive abstractions, events and signals. And the two can be converted to each other and are composable. We all know what events are, so let me briefly explain what signals are. And as you see here, they are called time-changing values. That means they reevaluate, they are computations that reevaluate automatically whenever values or simple values or other computations change on which they depend on. To put it more simple, you could think of reactive abstractions as just a third evaluation semantics. So we have eager evaluation, we have lazy evaluation, and now we have reactive evaluation. Reactive functions are not explicitly called with new inputs. They get automatically executed whenever their inputs change. Now, signals are first-class values in REScala. They can arbitrarily composed with each other, and we can use also predefined combinators for this purpose. The key is that changes automatically propagate through dependent computations in REScala. You can think of a REScala program program is similar to an Excel sheet. You change a cell and all other cells that depends on that cell get up to date automatically. Let me give you a glimpse of how REScala programs look like. Here is a piece of code modeling a to-do list. You don't need to read the code. I will point you to interesting things in there. Basically, we define several reactive values like remove all and create to-do and create task and a task list. These are values of type event or signals. And then finally, we call UI.display with task list as a parameter. Some reactive values are used to define other derived reactives, like for example, remove all is used to define a task list. And these used-in relations are depicted here by the white arrows, which basically depict the change flows. Whenever, for example, the task list changes, the UI display is executed automatically. There is no callbacks in this piece of code. No callbacks is needed to make UI display execute whenever a task list changes. How is this enabled, or what is the how behind the scenes? Well, basically the compiler creates a so-called dependency graph. The nodes in this graph encapsulate reactives, user-defined reactives. The source nodes, or the simple reactive values, are represented by triangles, while derived reactives are represented by circles here. So the key point is that, as I said, the graph orders computations according to their dependencies and encapsulates user-defined reactives. The execution itself, so when some changes come from the surrounding world, the execution is managed by the propagation algorithm, which starts re-evaluating the nodes that need to be changed, and then subsequently all derived nodes from those that are changed. As a result, user-defined reactive computations get invoked. The execution happens in the topological order of the graph, so the nodes are visited in a topological order. I mentioned that changes are propagated automatically and consistently. What does that mean? Let me explain what that means. So starting with the application in a consistent, let's say, resting state, with derived computations all up to date with their inputs, each input change is propagated instantaneously through the entire graph, as if it was an atomic operation, and it moves the whole application to a new consistent resting state in one step, in one instant. This is also called synchronous semantics. Technically, this is achieved by having at each node in the graph re-evaluating only when its inputs have already re-evaluated. This is basically this topological order in which the execution unrolls. Or it is also called glitch freedom. So this is illustrated by this flow here, where we have a node in the middle of the graph that is reached from a changed input via two paths. Nevertheless, this re-evaluation of this node will happen only once. And this is important for our REST discussion in the talk. This synchronous semantics of updates makes it easier for developers to reason about their programs. We have shown this in empirical studies, which have been published at TSE. And to conclude, I mean, this is it about the basics, and to conclude that part, just keep in mind that with reactive abstractions, we get a paradigm shift from programmatic tracking of dependencies between computations towards an automated flows of changes through dependent computations. And this improved capability of reasoning about programs that is enabled by the dependency graph, by these explicit dependencies captured in the dependency graph, is not only a nice feature for the programmers, it is also key for enabling the language machinery to reason about programs, so it manifests application-level semantics to the language machinery, which the machinery uses, for example, to automatically ensure correctness in presence of concurrency. So if we have flows that run concurrently, here, for example, the orange and the green flows, they run concurrently, but if they share nodes in the graph, then there is a conflict. We lose this synchronous semantics if we don't coordinate. So we need to ensure somehow that these concurrent flows appear as if they happened one after the other. And we do so with a very simple trick. Basically, we think of those flows as if they were transactions in the sense of database transactions. So each flow is encapsulated by the machinery into one transaction, and then the machinery ensures that transactions, even if they happen concurrently, they move the state of the entire application in sequential states, starting, for example, with the state phi, we have a transaction A moving the whole application to state A, and transaction B moving to state AB, and transaction C then to state ABC. We prove in that paper that I showed in the beginning of this part of the talk, formally, that the machinery ensures abort-free strict serializability, so a very strong consistency property. Especially this abort-free feature is not easy to ensure in traditional transactional systems. And we do so, more importantly, in a syntactically and semantically transparent way. So we create semantically and syntactically transparent illusions, also with affordable performance, as I will mention very briefly. In order to achieve this strong consistency property and do so in a very transparent and affordable way, the language features are key. So what are the language features that support us in achieving these results? Well, first, the explicit data dependencies, the topological order of the evaluations, this write-once semantics, and the fact that application state is encapsulated in reactive abstractions in REScala. Explicit data dependencies allow us to determine, or allow the machinery to determine re-evaluations, their schedule ahead of time, before actually executing the re-evaluations. And this is key in enabling us to avoid deadlocks and hence avoid aborts. The topological order of evaluations preserves this feature, the deadlock and abort-free serializability, even when the dependency graph changes dynamically during the execution, which is possible in REScala. So this beige apricot color stands for semantic transparency, because if you have no aborts, then it's impossible to distinguish the behavior of a program running on a single-threaded versus the same program running in a multi-threaded setting. The write-once semantics, or the glitch freedom, allows these transactions to execute in a pipelining mode. So as soon as one of the flows writes a value, it's certain that this value will not change anymore during this flow, so it can commit that value, make the value available to the other transactions or to the other flows. And this pipelining improves or helps with ensuring good performance, hence affordable illusions. And the final point, this encapsulation of application state in reactive abstractions is key in enabling syntactic transparency, because basically we can exchange the propagation algorithm without the need to change anything in the program code. What is more, we have also enabled these serializable flows in a distributed setting. So in cases where the data flow graph is distributed across several computing devices, and the flows are also distributed across several distributed devices. And we keep the property, and of course in that case it's not that easy, it's more complex to keep serializability, and we need more, we need a little bit of distributed coordination in this case, but only for transaction graph testing. So we have minimized consistency mechanisms and made them actually, they are buried into the system and not available to application developers to use, to quote again James Hamilton. This is all good. We have minimized the need for coordination, but nevertheless, there is this minimal part in the system that needs coordination, and we know that fast transactions are impossible when we have partitions. So the part of the system where we need coordination does not tolerate partitions, which may be unacceptable for interactive distributed applications we are considering here. Moreover, recall that I told you that there are so-called asynchronous problems, so problems that can be solved in a distributed setting without consensus. For these scenarios, we developed a partition-tolerant distributed update propagation, or so to say, we enable partition-tolerant flows which are consistent, and I will explain in a minute which kind of consistency they ensure. To this end, we make use of CRDTs, conflict-free replicated data types, and encapsulate them into reactive abstractions. CRDTs are data types whose state domain is a join semi-lattice. So the join operation is associative, commutative, and idempotent. Okay, the distributed property is added by Joe Hellerstein just to make the acronym at the end read ACID, so as to allude to the ACID property of databases, but so you can forget about it. So associativity, commutativity, and idempotent properties. These are the mathematical properties that enable diverging CRDTs to be merged without consensus, but with strong eventual consistency guarantees. A very simple CRDT is a set data type with a union operator, but one can implement many data types as CRDTs. People have done so. There are libraries out there, or even entire databases like REAC based on CRDTs. And there are languages, domain-specific languages, that support operations for composing CRDTs. And recent work on mergeable data types shows how to derive CRDT implementations out of invertible rational specifications of inductively defined data types. Now back to REScala. CRDTs are encapsulated into reactive abstractions. I mentioned this, and we call the result conflict-free replicated reactives. For illustration, you see here the same example, the to-do list, but now replicated, and the only difference to the program that I showed you before is that we have replaced some data types, or two of them, like here with the to-do data list and to-do list, the task data list and to-do list are now conflict-free replicated signals. So now we have basically distributed graphs that are connected via replicated reactives. Here the pentagon nodes, wherever in the part of the system where we have unreliable network connections, we use these replicated reactives. And the conflict-free replicated reactives, they behave locally like normal reactives, so changes propagate through them as they propagate through any other local reactive. The replicated reactives broadcast, in addition, their changes to their replicas, and they also propagate not only changes to their local inputs, but also the arrival of new versions from their remote replicas. Overall, the broadcasted changes may arrive in different order at different hosts, so clearly this does not provide transactional consistency, but we do ensure strong eventual consistency for the entire application without any remote coordination. By end-to-end, I mean the entire application, and actually we prove causal consistency, so a stronger consistency guarantee than a strong eventual consistency, theoretically, but in REScala itself, in the implementation, we just guarantee only strong eventual consistency for performance reasons. The picture in this slide basically indicates how things look like with REScala applications, distributed interactive applications written in REScala. So the state is distributed across devices and data centers. Parts of the applications may have stable connections, like here on the right. Other parts may have unstable connections, like on the left. And the state in this left part may temporarily diverge between devices, let's say, and the data center or the devices among each other. But these diverged states will eventually be merged into a consistent state. And once in a while, consistent state is stored in local memory and local storage to account for crashes of the devices. Once this happens, stored snapshots are kind of reloaded, and the recovery is basically just another reactive flow. So even for this part of the system, snapshotting and recovery, we do make use of the reactive programming features to minimize the amount of data that needs to be stored, and also to model recovery just as reactive flows. Now, recall I told you that we ensure end-to-end strong eventual consistency, which means the guarantees of individual CRDTs extend to the entire application state. The question is, how do we do this? An application typically consists of several CRDTs, and state changes of related CRDTs must happen atomically, not automatically, but atomically, to retain causality. To achieve this, one would typically need to merge nest CRDTs to create new composed CRDTs, hence losing modularity. This is not necessary with conflict-free replicated reactives due to transactional flows. These transactional flows, you recall, they move the entire application instantly from one state to another bigger state. Hence, they ensure that changes to related CRDTs in the program happen indeed in one instant as an atomic operation. To illustrate this a little bit more in detail, let's look at this picture here. So assuming we have two devices, I'll call them D1 and D2, the execution starts at some consistent state. Time passes or moves here from left to right. Boxes present different application states in device D1, and circles do the same for device D2. D1 executes transactional flow A and then transactional flow C. D2 execute transactional flows B and C. State transitions are represented by filling the boxes in pink in device D1 and coloring the outline of circles in device 2 in yellow. So what happens here? D1 moves first to state A by executing the flow A. Then it moves to state AC when C finishes its execution. D2 moves to state B and then to BD. Now device A, when it is in state, device 1, when it is in state A, propagates its current state to device D2, which arrives at D2 while it is in the state BD. The state A of D1 is merged with BD into a new state ABD in device D2. Also, D2 propagates or broadcasts its state BD to device D1, which arrives at D1 when D1 is in state AC. So AC and BD are merged in D1 into a new state ABCD, and eventually these two merged states are merged into the next consistent state ABCD. So please notice that what we get at the end, this state transition system here, is basically a lattice. So the entire application state itself is a CRDT, and we proved this in the UPSLA 2019 paper. Now, where do we stand? So, applications in REScala can be built with distributed transactional flows. For example, those parts of the applications that run on stable connections. This requires minimal synchronization, but yet there is some synchronization, so this part of the application do not tolerate partition, but it's okay to employ those transactional flows in parts of the distributed systems where we know partitions are rare. In parts of the distributed application where connections are not stable, we can use these consensus-free, hence partition-tolerant flows, which are consistent, meaning they ensure strong eventual consistency. So, given that these two different kinds of flows are supported under or in the context of a unified program model, it's rather easy. So let's put it this way, they can be composed within the same application. However, it is the responsibility of the application developer to do this composition, and you know, I have said it several times that I don't find it a good idea to put too much responsibility on the application developers for the sake of getting things correct, but also for the sake of productivity, for taking burden away from application developers. So this is something we are working on right now, and to this end, to achieve the goal of making the combinations of, or the compositions of strong consistent and eventual consistent flows happen automatically, we make use of behavioral specifications. What are those? Those are pre and post conditions of transactions and application level safety properties, invariants. So given an input program and some behavioral specifications, these are the inputs to our language integrated decision procedure based on some data flow, which is very easy in our case because the data dependency graph is explicit. And based on the behavioral specifications, we generate some verification code, which then is passed to a program verifier, which outputs the so-called synchronization points. So those are the transactions or the flows where we need synchronization. With this, let me summarize, come to an end of my talk. I started by saying that today's computing is massively distributed and out of control, and that consensus is very challenging in this setting. I concluded the first part by saying that we need new affordable illusions that maximize the combination of consistency and availability, and that PL-based automation is needed to bring different angles on this combination together. In the second part, I presented you one such PL-based approach, the REScala programming language, and I hopefully made clear that our weapons to automate affordable consistency have been features of the reactive programming paradigm, functional reactive programming, and more recently also application level behavioral specifications. This said, the journey doesn't end, of course, here. There are many ideas to investigate in the future. We are considering, for example, even more disordered systems relying on disruption-tolerant networking. An interesting thing would be to look at seamless integration of transactional flows and database transactions. Think of reactive nodes encapsulating entire databases, or we are looking at ways to encapsulate complex event processing, versatile complex event processing semantics, and ML, machine learning semantics, into reactive graphs and even more.